This maps a basic cloud storage architecture. Users connect through a load balancer to API servers, routing data to storage. But this fails during simple edits. Changing one character in a 10 GB video forces the client to re-upload the entire 10 GB file. For a service with millions of users, pushing monolithic files for minor edits saturates network bandwidth and generates unsustainable infrastructure costs. Building a production-grade sync system requires adhering to 4 strict engineering rules. Rule 1. Only transmit the specific bytes that changed. Rule 2. File metadata must maintain strong consistency across the database layer. Rule 3. Clients require instant alerts when a file updates. Rule 4. Network failures must not result in lost or silently overwritten data. To survive at this enormous scale, the system must break down and abstract these monolithic files into much smaller, discrete mathematical blocks. This schematic introduces a dedicated block server sitting between the client and cloud storage. Its first task is slicing an incoming file into fixed-size chunks, typically capped at 4 megabytes per block. Each block is then compressed and encrypted independently before being transferred to storage. We could offload this processing to the user's phone or browser hardware, but centralizing this heavy lifting on the server provides significant engineering advantages. Maintaining identical chunking and encryption logic across iOS, Android, and web platforms creates a massive maintenance burden and introduces version-specific points of failure. Furthermore, client devices are easily manipulated. Critical security and encryption protocols should reside on the server, where they cannot be bypassed by a compromised client. This centralized approach enables Delta Sync. The system handles edits by comparing hashes of the user's local blocks against the server's known hashes. Using this algorithm, only the modified blocks move over the network. This also optimizes storage. If multiple users upload identical content, the server recognizes the existing block hashes and simply references the data already in S3. These blocks transform a 10 GB upload into a transfer of just a few kilobytes, removing the system's primary bandwidth bottleneck. Eventual consistency is sufficient for raw block storage, but the file metadata offers a different approach. If metadata caches disagree on version histories or permissions, the system risks routing the wrong blocks to the user, causing data corruption. This database schema tracks files as relational pointers to an ordered list of specific blocks. The file version table acts as a read-only ledger, preserving the block order of every past edit, so any previous state can be reconstructed. When a client initiates an upload, it sends parallel requests to the API server for metadata and the block server for data. The API server records the new metadata in the database and marks the file status as pending. Simultaneously, the block server finishes chunking and pushes the encrypted blocks to cloud storage. After the blocks are secured, the cloud storage triggers a completion callback to the API server. Only after storage is confirmed does the metadata database update the file status to upload it. This two-phase commit makes the database the absolute source of truth. If the database does not confirm the blocks, they don't exist to the user. A notification service must instantly alert distributed clients the moment a file changes so they can fetch updates. Long polling maintains a persistent connection between the server and online clients, providing real-time updates without the overhead of WebSockets. We also have to account for users who edit documents while disconnected from the network. We route those alerts into an offline backup queue, which stores the notifications until the client restores its connection. Upon reconnection, the client pings the queue, pulls the missed metadata, and downloads the specific blocks needed to sync its local state. When 2 users edit the same file simultaneously, they create a concurrent sync conflict that the system must resolve. The resolution strategy is simple. The first version fully processed by the server wins. Because user 1's request was processed first, the server rejects user 2's update due to a version mismatch. A reliable storage system cannot silently overwrite or discard a user's work. The architecture preserves the rejected data by creating a conflicted copy, forking the document to save user 2's local edits as a separate file. The UI presents both versions to the user, requiring a manual review to merge the changes. This process handles file synchronization. Real-time collaborative editing relies on different algorithms, like operational transformation. The long polling notification service ensures that as soon as a change is committed, other clients are prompted to handle any resulting conflicts. Distributed synchronization relies on a choreography of rigid rules that prevent data loss when concurrent edits occur across different devices. This diagram represents the fully assembled architecture required for a production-grade sync system. Success in system design is measured by how gracefully the architecture handles failure across these decoupled components. If a block server fails mid-upload, the client retries. If the database rejects a commit, orphan storage blocks are safely removed by garbage collection. Maintaining this requires monitoring sync delays, compression ratios, offline queue depths, and failed block writes. Block-based Delta Sync reduces bandwidth consumption, while a strongly consistent database ensures every client sees the same file hierarchy. Push notifications maintain device parity, and durable cloud storage protects user data from loss. Guaranteeing correctness under failure is the essential function of a storage system. Designing it correctly prevents massive bandwidth costs for even the smallest file update.